In a binomial distribution, we have this nice formula where we talk about the number of trials, the number of successes, and the probability of success and the probability of failure. And what that gives us is basically in that binomial experiment, in that binomial distribution, what the probability of something happening. A lot of work, not necessarily hard work, but it is a lot of work. So, good news. Instead of using this formula, we all have a copy of, well, I'm just calling it Table B. And I'm actually not calling it that. That's what it's being called in the information I have. And we're able to solve problems using that table. Now, we still have to identify our variables. We need to know how to use the table, but it's going to save us doing all this work. So if you remember in the past we've done where a coin is tossed 3 times, find the probability of getting exactly 2 heads. So, real quick, what we came up with was we had a sample space of 8. If you remember, we had heads, 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 tails, and you get the idea, heads, tails, heads. Anyway, there was a total of 8, and we wanted exactly 2 heads, and that worked out to be 3 out of the 8. And if we did 3 out of 8, that was 0.375. Okay, here's what I want you to keep that in mind. We can read a table. Now, to read a table, this is what we need to know. We still need to know the number of n, so our number of trials is 3. We need to know what we want our success to be, exactly 2. And we need to know the probability of that success. Well, remember, for flipping a coin, it's 1/2 that we're going to get heads, or change it to a decimal. So we're going to take this information right here, and we're going to use our table. Notice we have, this is the binomial distribution table, and this is just a small portion of it. We have our number, our n right here. In fact, let me put that up here. Not that. Well, let me just write it. Our number of trials was 3 coins. Our success, what we wanted to find the probability of, was getting 2 heads, and that probability for that was 1/2, or 0.5. So here's what you do. Find your n, find your x, and then find your p, and our p is right here. So we kind of just have to see, well, let's do this, where it all works out. So here is my number of trials, 3. Oops. Success 2. Here is my probability of getting 0.5. And right here, what we see is that it works out to be 0.375, which is what our probability was. Yay, good news. We don't have to use the formula anymore as long as we have the binomial distribution table, Table B. So I'm going to be referring to this table in the next few examples. Public opinion reported that 5% of Americans are afraid of being alone in the house at night. If a random sample of 20 Americans is selected, find these probabilities using the binomial table. All right, so let's start with part A right here. Now, identify the 3 things we need to know. We need to know our n, number of trials. Well, there was 20 Americans selected. What we want to find the probability of. And we want to find the probability that there is exactly 5 people. So our random variable x is 5. And our probability is 5%. So if you were to grab your table, and I'm going to write 5% is 0.05. And just like we did here, find your n, find your x, then find your probability and see where that meets. We get that the probability of exactly 5 people is going to be 0.002. Way easier if you have your table than trying to figure out all that using the formula. Not that we couldn't, but a little bit easier. But notice what happens in B and C here. We start throwing in the words at most and at least. So let's think about what at most means. All right. What is my number of trials? Well, that's still 20. What is my success? Well, let me jump right here to probability real quick and write that down because that's not going to change. At most, if that's at most it can be, that means it can't be anything higher than 3. But it could be 0, could be 1, could be 2, and it still could be 3 because at most it can be is 3. So basically when you have something like this where it says at most, you're still going to use a table, but you find the probabilities of each of the parts. Probability of 0 being chosen, of 1 being chosen, who are afraid of being alone at night, 2, and 3. Use your table then. So you're going to use 20, x is 0, and then 0.5. And you come up with, I'll write it over here, 0.358. And then you use your table again, 20, x is 1, probability is 0.05, and you get 0.377. And if you keep doing that, right there. Remember, we're adding them all up because they are independent. And that's what I'm doing here. I'm taking the individual probability and adding them up. And you type that into your calculator and you get a probability of 0.984. So almost 90 or over 98%. When you take your sample of 20 and at most 3, it's going to be about 98%. What about at least? Well, again, our number of trials is 20. Our probability is going to be that 5%. But what does at least mean? Well, at least 3 people means it could be 3 or 4 or 5 or blah, 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 all the way up to 20, because that's the number of trials we're taking. We could absolutely do it like this. Find the probability of 0, 1, 2, 3, 4, 5. Actually, no, sorry, we wouldn't find the probability of 0, 1, 2, 3. We'd start here. Find the probability of 3, 4, 5, 6, 7, 8, all the way up to 20. Totally can be done. But think in the past when we've worked with the word at least, we've done that 1 minus, okay? So when you see at least, what we can do is 1 minus the complement. The probabilities that it's not, and I think we notated this with a little line over it, I think. So we can take the complement. What does that mean? Well, let's take the probabilities of 0, 1, and 2. It's a little bit shorter, and they don't fall in here, and then go 1 minus that. So the probability of 0 is 0.358. The probability of 1 is 0.377, and the probability of 2 is 0.189. When you add all that up, we get 1 minus 0.924, which is going to equal 0.076. So what is our probability of at least 3 people? 0.076. Okay, so it's not a real strong probability when only 5% of Americans are afraid to be alone, and we're taking 20 people, and we want at least 3. It's not really strong probability. Again, we could have found the probabilities of each of these individual pieces all the way up through 20 and add them together, or use the idea of a complement and the fact that our probabilities, successes and failures, have to add to 1. Since it says at least, well, let's assume the probability of 0 people, 1 person, and 2 people, and then go 1 minus that. One last example. A report from the Secretary of Health and Human Services stated that 70% of single vehicle traffic fatalities that occur at night on weekends involve an intoxicated driver. If a sample of 15 single vehicle traffic fatalities, and I'm not going to be able to say that, I apologize, oh my goodness, that occur at night on a weekend is selected, find the probability that exactly 12 involve a driver who is intoxicated. Okay. Despite my inability to speak correctly, we can still pull out the needed information. Number of trials, that's 15. They're taking a sample of 15. Successes, they want exactly, that word exactly 12. And the probability of a single vehicle traffic fatality, there we go, knew I could say it, is 70%, which 0.7 or 0.70. Using the table. And if you need help understanding the table, please come talk to me. Find your n of 15. Find your x in the n of 15. That's 12. And our probability of 0.7. And you are going to get 0.170, about 17%. Using the table is doing the same thing as the formula. It's just a nice shortcut method, especially when we're throwing in the words at most and at least.